Hello and welcome to this short video tutorial going through longitudinal and transverse waves. This is your first lesson in the waves module, and I'll go through your worksheet, which was the activity for last week, as well as trying to demonstrate some of the ideas using a waves simulator at the same time. So please watch through this, go through your worksheet, check if there's any answers you need to go and correct, or just kind of know that your understanding is right and they're correct, and obviously edit it if you need to. So what I'll start off with is just these properties here. Amplitude is, wavelength is, time period is, frequency is, and in order to have a better look at that, I'm just going to switch over to this wave simulator. We're going to set that to oscillate, and what we essentially have is a wave on a string. Now this bit that's doing the oscillating shows that essentially if I just pause that and go frame by frame for a second, it shows that all that's happening to this end of the string that's free to move, that one's fixed, this end that's free to move is just bobbing up and down. Okay, that's all it's doing. It's not being moved in any other way other than up and down. Now what's also quite interesting is if we have a look at these green particles on the string, which are essentially just markers. You can look at any of the particles, but we'll try and focus on those green ones. Are the particles of the wave, is the matter that makes up the wave actually moving to the right hand side? Because if I let that play, it looks like the wave is moving to the right hand side. But if we just track these green particles, all that they're doing is going up and down. They're not actually moving across the page. So what's happening is energy is transferred through this one, which is a transverse wave, to the right hand side, but the matter itself, the particles themselves, aren't moving other than vibrating up and down. So what we have is vibrations up and down, which are 90 degrees or at right angles to the direction of the wave, because the direction of the wave is to the right hand side. So you've got this right hand side wave direction, but this up and down motion, meaning there's a 90 degree angle between the wave direction and that direction of motion. So I'll let that play for a little bit more. Let's just have a look at what happens if we increase the amplitude, and then we'll go for a really decreased amplitude as well. So increased it, have a look at the waves seem bigger. If we go and decrease it, the waves themselves are smaller, but that rate of oscillation has not changed. So let's just move that back to around where it was before, about 0.75, and let's have a look at decreasing the frequency. So the waves are still essentially the same kind of height, but there's less of them, and we can now see that the oscillator is moving a lot more slowly. And if we increase it, then there's a lot more of these waves and the oscillator is moving very, very quickly as a result of that. So let's use that. Let's go back to those definitions and have a look at trying to understand what each definition is, and use what we've just learned from the simulator and apply that. So amplitude, out of these, think about what happened when we increased the amplitude. The waves looked like they were a lot bigger, and that's essentially then saying y, which is the distance from the rest position to the top of the wave. Let's have a quick look back. This dotted line or dashed line is the rest position, and if we just pause that, that top of the wave to the rest position is the amplitude, or the bottom of the wave to the rest position is the amplitude. So it could be from rest position to peak, or rest position to the trough. And if we decrease that amplitude, you'll see in a moment what happens to the distance between the rest position and those peaks and troughs. Let's try and get a bit of a wave shape there that we can go and measure amplitude with. So a much smaller amplitude that time, from peak to rest position and from trough to rest position. In terms of wavelength then, that's fairly more, it's a bit more easy to go and work out from these definitions. So it's essentially going to be z, which is the distance from one point on the wave to the identical point on the next wave. Let's have a look at that using the simulation as well. Just let that play. Let's have a slightly bigger amplitude, and if I pause it there, from here, this trough to this trough will be the one wavelength, or from this peak to this peak will be one wavelength, or that peak to that peak is one wavelength, or this rest position, not to the next adjacent rest position, but the one after, because that, if you follow my mouse cursor, that's one complete wave, so one whole wavelength. Time period is, you probably would have worked out there from where it says the time for one wave to pass a given point, so x, and the frequency, as we saw, is the number of waves or oscillations per second, which is w. The following diagrams show you essentially a longitudinal wave and a transverse wave. Remember, the wave on a string was a transverse wave because we had those oscillations or vibrations at right angles to the direction of the wave. So which type of wave contains compressions and rarefactions? You can see from the diagram that that one there will be, let's just wind that back, it will be longitudinal. In fact, what I'll do, just to make it easier to compare these answers with the ones on your worksheet, I'll just highlight these in green. Okay, on to the next one, where it says waves travel parallel to the direction of vibration. Again, just having a look at the diagram and think back to the waves on the string, we know that for the transverse wave it's at right angles, so it can't be that one because right angles is not going to be parallel. Sorry, that would be perpendicular. So it's going to be our longitudinal wave again. And then we'll move on to 2C and 2D. It says something waves are made when the oscillations are at 90 degrees, and that's ideal because we've just been looking at the simulation, which is our transverse waves, similar to the one on a string. And sound is caused by something waves. You may have read about this in the textbook pages or the PowerPoint that I may have attached. In the textbook pages that I attached. And sound is caused by longitudinal waves. And essentially what sound is it's the compression of air particles vibrating against each other in this sort of format in a longitudinal wave until they reach your ear. Fill in the table below to show if the observations apply to longitudinal, transverse, or both. Put yes or no in the correct boxes in the columns. So these waves transfer energy. Yes and yes, both of those do. And again, I said I'll colour code that just to make it easier to review. The direction of vibration is at right angles. It is for transverse, but it's parallel for longitudinal, so that's going to be a no. Sound waves are this type of wave. Let's just look back at 2D. Sound is caused by longitudinal waves, and so here for transverse we can put no, for longitudinal we can put yes. And these waves can travel in a vacuum, and light waves are this type of wave, and that is transverse. Light waves, all EM waves are transverse and can travel in a vacuum. So we'll go with yes and no. Okay, for A to D, it says these waves can be described in terms of their wavelength, frequency and velocity. And what we can put here is both. They both have a wavelength, frequency, and can travel at different velocities or speeds. Okay, 4B, when I dropped a stone into water, ripples were formed. These are transverse, and they're transverse waves because the vibration of the water, or even water molecules, water particles, are at right angles to the direction of the wave or the ripples. Okay, so it's sort of about that 90-degree angle. These waves allow us to communicate with each other. We could put both here because transverse waves, or we could put actually EM waves, are transverse and are used in lots of communication methods. By EM waves, that would include light, so by signaling with light, that would be using transverse waves, or using Wi-Fi with microwaves, that would be transverse waves as well, and so on. But also, one of the methods that I'm using right now is talking, and that's essentially longitudinal wave, because we said, just going back, longitudinal wave, sound waves are this type of wave, yes. So you can just add in here that sound waves are longitudinal. All of these waves contain an electric and magnetic field. Well, not every single transverse wave has an electric and magnetic field, but all of the waves that have an electric and magnetic field, which are EM waves, they are transverse. All EM waves. And EM, as you might have just seen there with the predictive text, is electromagnetic waves. Electromagnetic because it's electric and magnetic field that makes it up. And there ends this video tutorial. As I said, please make sure that you do watch it. Go through your, and as you've watched it, you've been going through your worksheet just to check your answers, make corrections if required, and hopefully the simulation was useful as well. Until next time, take care.